Good morning to all of you. As she said, my name is Umesh Tiwari and I represent Malvern Panalytical here. I'm based in Singapore for the last 10 years or so. My background is physics. I did my PhD in physics long time back. And then for 4 years, I was in a defense laboratory. And then in 2003, I joined Malvern Panalytical to begin with as an application specialist. So my background is application specialist. And now I am part of the advanced material sector, looking after the energy and environment segments within Malvern Panalytical. Today I will present you about the X-ray solutions, which is the X-ray fluorescence and X-ray diffraction. And that will complement with what my colleague will present later on our morphology solutions. So this is the structure of my presentation. So all the morphology solutions details will be presented by my colleague Joy. I will give you a brief overview of our overall solutions within the battery research and R&D, and production. Then I will come to the XRF solutions and the XRD solutions, and finally some concluding comments. So the lithium-ion batteries, just a brief introduction about what kind of materials we are talking about that will be analyzed by these X-rays. So in the lithium-ion batteries, you have 4 major components: the cathode materials, the anode, separator, and the electrolyte. So the X-ray solutions are mainly for the cathode materials, anode materials, and the separator. Not much for the electrolytes. So in my X-ray solutions, I will be talking about the materials and the battery cells, but in relation to the cathode, anode, and the separator. So for the battery cells, because again we are talking about the X-ray solutions, and particularly for XRD, it is about the crystal structure. So there are 3 main kind of cathode materials that are present in our current production commercial batteries. That is the lithium cobalt oxide based. Of course, the cobalt can be substituted with nickel and manganese. So the most popular chemistry nowadays is the NCM 811, where nickel is 80%, cobalt is 10%, and manganese is 10%. Because this chemistry gives you the highest energy density. Although to stabilize this chemistry, there is some kind of art and some kind of IP technologies that are involved. It is not so easy to stabilize this chemistry, but once stabilized, that gives the highest energy density. Other is the spinel, which is LIM M204, but this is more for the smaller kind of batteries, not much used in the electric vehicles. In the electric vehicles, another chemistry that is in use is the LiFePO4, lithium iron phosphate. The advantage of this chemistry is that this has a better safety than the NCM. It is more stable kind of material. So from the safety point of view, when you have higher temperature and lower temperatures, so this chemistry is more safe. It will not catch the fire. The disadvantage is that it has slightly lower energy density compared to NCM. So for the NCM 811, you can reach energy density of 250 kilowatt hour per kg. For the LFP, it is about 150 kilowatt hour per kg. So there is an energy density difference, but it is a very safe chemistry. So many people say that for the environment that exists in Asia, that is more hot kind of climate, maybe LFP is a better chemistry, although it gives slightly lower performance. For the anode materials, the commercial use material is the graphite, and in all commercial batteries that are available today, the graphite is the anode material. But people are trying to use other chemistries. Again, this Li lithium titanate, titanium oxide is used. Again, it makes the battery more safe, and it makes the battery to charge much faster and also have more lifetime. So if you are using this as the anode, you have the better lifetime, faster charging, and more safe batteries. But there is a cost that energy density is lower. So if where you don't require high energy density, then this material has a lot of advantage. And for example, Toshiba has, I think, patents on this technology, and they promote this as the anode material. Another anode material that is being researched that is more in R&D is the silicon, nanosilicon. Nanosilicon has about 10 times more energy density compared to graphite. But again, the material is not stable. As such, it is stable, but once you charge discharge, once the lithium ions go into it, it expands too much, and then the particles can start cracking. So it is not a safe kind of material. So it is still in R&D, but there are some breakthroughs that either mixing with graphite or making it porous kind of silicon that even if it expands, there is a space for that. So in the next 3-4 years, most likely silicon will replace the graphite. Okay, now coming to our solutions. Starting from the precursor materials, because usually when you synthesize these materials, you directly don't synthesize the final cathode material. You start with some precursor material. For example, if it is NMC chemistry, then precursor material will be NMC hydroxide. So nickel, cobalt, manganese, and hydroxide of that, which is then synthesized from the pure kind of sulfates of nickel sulfate, cobalt sulfate, and manganese sulfate. Then you convert this, mix it with lithium, and make the final cathode material, which is with the lithium NMC oxide. So for this, we have a range of solutions because these are powder materials. So the particle size plays a role. Particle shape plays an important role. Crystal structure is very important, and the chemical composition, because if it is NMC, say 811, then you would like to have 80% nickel, 10% cobalt, and 10% manganese. So the chemistry becomes very important for these powder materials. When you to make the battery cell, then this powder material is turned into a slurry, which is coated onto the current collectors. So here again, the slurry rheology, you have the rheometer here, with which you can measure the rheological properties of the slurry. But these rheological properties are very interlinked to the particle size and shape. So if you want to change the rheology, only way is to change the particle size and shape. And of course, you can also change the formulation. And then you have the battery cell. In the battery cell, we have a special technique that is called the in operando XRD, that during the charging, discharging of the cell, you can look into what are the phases, how the phase is changing inside the battery, how the structure is changing. And from that, you can derive or you can predict whether this battery will give you good performance or not with the charging, discharging cycle. So we can do that. And finally, for the end use, again, when these materials are being recycled, elemental composition is the most important because that has the value. That is how the value of the battery comes. But other parameters like the particle size and crystal structure are also important. Okay, just 2 slides about an overview of our solutions, why these are important. So as I said, for the powder materials, particle size distribution is very important. And the reason why it is important is, in general, small particles give you more power density, and the larger particles give you more energy density. And in a car, you need both. You need power density means better acceleration, and more energy density means more mileage. So you need both. So you need to optimize or have a distribution of particle sizes which are small and large, so that you can get the optimal power and you can get the optimal energy density or the mileage. So to measure the particle size distribution, we have the laser diffraction. My colleague Joy will talk more about that in the next presentation. Then the particle shape is also important, because when you turn this into the slurry and you want to coat it, you can get a better energy density if your packing density is more. And this packing density is governed by the particle shape. And also the rheology, how homogeneous this coating is, that is governed by the particle shape. Usually in battery chemistry, in the battery, spherical particles are desired because spherical particles give you more packing density. Any deviation from spherical particles will lead to inhomogeneous coating as well as less energy density. So people want to have spherical particles. Even for the graphite, although graphite has a very long C-axis, naturally it does not exist as spherical particles, but then they agglomerate many particles to make it a spherical particle to get a better property. If you have nanoparticles, then we have another technique that is called the dynamic light scattering. And so that can measure the nanoparticles better. Laser diffraction is more for the micrometer particles, although it can measure from 10 nanometer to about 3 millimeter. But below 100 nanometer, then zeta sizer becomes this dynamic light scattering is a better technique. And this also has the zeta potential. That means in the slurry, you can measure the stability of the slurry, whether the particles will stay dispersed or they will agglomerate. So if they have the tendency to agglomerate, the zeta potential can tell you that, oh, this slurry will not be stable. Then we have the X-ray fluorescence. X-ray fluorescence is a technique that measures the elemental composition. So whatever is your chemistry. X-ray diffraction is the crystal phase analysis. I will come to in more detail about these two techniques. And finally, we also have GPCSH, which is a size exclusion chromatography. And this is to analyze the polymers that are present as a separator or as a binder used in the batteries. So using this, you can measure the molecular weight, you can measure the molecular size, you can measure the branching, which are important parameters when you use it as a separator. Okay, so this was a brief overview, and now I come to the two techniques, the X-ray based techniques that I will discuss in the rest of the presentation. The first is the XRF. XRF is a technique that measures the elemental composition. So you can measure it either as pure elements or you can measure it as oxides. And you can measure it in different kind of materials. It can be solids like this. It can be liquids, powders, filters, for example, that are used in environment, or the fuse beads. So the technique is pretty simple in principle. The principles of the technique that you have a source of X-rays, so high energy source of X-rays that falls onto your sample. So these high energy X-rays are falling onto your sample. These X-rays knock out the inner shell electron, either the K shell or the L shell, and then the outer shell electrons fall and they generate secondary X-rays, which is characteristic of your element. So it can excite the X-rays from your elements, and then you get this kind of spectra, which is for every energy, it is representing a different element. For example, for the at 6.4 keV, it is the iron. At 7.5 keV, it is nickel. So you know that what energy these secondary X-rays are coming, and they represent different elements. And from the relative intensity of these peaks, you can find out their concentration. So this is in principle the technique. There are other techniques that you can be used for the elemental composition analysis, and in particular ICP and the related kind of techniques, which can be ICP-MS, ICP-OES, or also the atomic absorption, and relatively they are positioned like this. ICP-MS, of course, can measure very low concentrations like down to PPT or even PPQ. So when you want to measure at very, very low levels, then of course it is always ICP-MS. X-ray fluorescence can measure from say about 1 ppm to 100%. And that is the advantage of X-ray fluorescence, that there is no other technique which can measure at very high concentration and at the same time at the lower concentration. So X-ray fluorescence can measure from 1 ppm level up to 100% level. All other techniques, then you have to dilute the samples multiple times, and only after dilution you can measure it. But with XRF, no dilution is required. You can directly measure up to 100%. And that is advantage is because most of these major elements are in few percent, and then you can directly put your sample and analyze with XRF. Limitation of the XRF is that the light elements are slightly difficult. So for example, in your lithium ion batteries, it cannot analyze lithium, although we can indirectly analyze it by analyzing all other elements, and then we say that whatever is remaining is lithium. So we can indirectly analyze that lithium, but not directly. Okay. XRF spectrometers, there are two types. One is the ED XRF, which we call the energy dispersive XRF. There the configuration is very simple. You have a source of X-rays, you have the sample on which this X-ray is falling. Then you have the secondary X-rays which are excited from your elements. And you have an energy dispersive detector which can detect all these X-rays, and it can classify into different energies. So it is an energy dispersive detector. So here we have the model that we have is the epsilon. Typically, ED-XRF can measure from fluorine to uranium, more typically up to from sodium to uranium, but some special kind of ED-XRF, they can analyze from fluorine to uranium or even down to carbon. For ED-XRF, you don't need high wattage because it is measuring all the elements simultaneously. So the measurement is really fast. So even the low power from 5 to 50 watts somewhere here is good enough for ED-XRF. Wavelength dispersive XRFs are more complex configuration, that you have the X-rays that again falls onto the sample, but then you have some collimators, you have analyzer crystals, and then it falls onto the detector. So you have two more components here, the collimator and the analyzer crystal. And this is called wavelength dispersive because this analyzer crystal diffracts the beam through the wavelength. At different wavelength, it will different. So it is a sequential kind of measurement. At one time, you measure only one element, then the crystal moves, then it measures the second element, then crystal moves, it measures the third element. Then maybe you have to change the crystal that will measure other three elements. So it is a sequential measurement. So this is slower than ED. And that is why to make it faster, you need higher power. So usually WD-XRFs are higher power from 1 kilowatt to about 4 kilowatt. The advantage of WD-XRF is that it has better sensitivity to light elements. So whenever you have light elements like sodium, aluminum, silicon, or below, particularly boron, carbon, and these kind of light elements, then always WD will perform much better. So if light elements are very important, then you go with WD. But otherwise, if you have sodium onwards elements, then ED is good enough. This is a benchtop kind of system because it is low power. This is more of a floor standing system, larger system. For the battery materials, because anyway, lithium cannot be analyzed even with WD-XRF. So even if you have WD-XRF, because the lithium does not emit, you can say in the X-ray range, it is more below X-ray range because it is very light element. So lithium anyway cannot be analyzed, and all other elements which are present, they can be analyzed with EDXRF. So I would say that for battery materials, unless you have a very high throughput kind of analysis, because WDXRF can take multi-sample changes, auto sampler. Otherwise, you can analyze it with EDXRF. So rest of this few slides I will show is on the EDXRF. So this is the model that we have. Epsilon 1 is the entry lowest kind of model, and then we have the epsilon 4. And here also there are two versions. One with the 10 watt version, which is 2 milliampere, and 15 watt version, which is 3 milliampere. And also in the higher version, another difference is this detector area. So this has a larger detector compared to these two. So because of this, this is, of course, can analyze elements from carbon onwards. This one can analyze elements from fluorine onwards, and this one can analyze elements from sodium onwards. So depending upon what is your requirement, you can select the model. But also in this epsilon 4, what we have implemented is the low kV excitation. So we can go down to 4 kV, and most of the benchtop XRF usually start from 10 kV. And that is an advantage, because with the 4 kV excitation, you can get better sensitivity to the light elements. And that is why we can go down in the light element periodic table. For example, with the sodium, magnesium, oxygen, you have more signal coming when you are using the 4 kV. And but for the higher Z elements, of course, for example, for phosphorus, then you have 10 kV excitation, which is better. In the epsilon 4, you can switch between different voltages. So you can use 4 kV, then 10 kV or higher kV, depending on what elements you are analyzing. And you can have the good sensitivity to the low Z elements as well as high Z elements. Okay, so that was about the XRF part, but XRF also important aspect is the sample preparation. So you can have many different kind of samples, but finally, if you want to get a good results, you can directly also analyze the solid, but the analysis would be more semi-quantitative. But if you want very accurate analysis, then you have to crush that into a fine powder, or unless it is a liquid, then you can directly analyze the liquid. Also, when you have this powder, again, you can prepare it in different ways. You can measure it as a loose powder. You can measure it as a press pellet, or you can fuse it as a glass bead and then measure the glass bead. The liquid sample, of course, you can directly put into the sample cup and you can directly measure. And then you put it in one of the XRFs. Usually XRFs require some kind of calibration. The calibration can be standardless calibration. We call it standardless because we provide some samples which are generic samples, and you calibrate the XRF with that. That we call the Omnian calibration. And then we apply all the theoretical corrections to correct for your matrix effects and everything to give you as good a data. But again, this technique is more semi-quantitative because it is not representing the matrix of your sample. So it is more of a generic kind of calibration. But you can also do with some reference standards. So these reference standards would usually have the same metrics as your samples. And we can provide the certified reference materials for the battery materials, any chemistry you are working with. So because we have our own accredited lab, which can make the certified reference materials to calibrate the XRF. Just like ICP, you are calibrating, you can calibrate the XRF, and we provide these standards. So you have the set of standards. You prepare the sample in one of these ways, put it onto the XRF, and then you draw this calibration curve. And once you have this calibration curve, then you can measure any of your unknown sample. Again, you prepare the same way as you had prepared your standards, put into the XRF, and that will give you the elemental composition. So it is a very straightforward kind of technique. and sample preparation, you don't have to digest into acids or those kind of things. You can directly measure just by pressing into a pellet. You can directly measure it onto the XRF. Of course, the accuracy of your results depends on sample preparation. If your sample is more coarse kind of sample, not fine ground, then you get low accuracy and you are measuring as a loose powder. If it's a fine ground powder and you are measuring as a loose powder, then you get better accuracy. If you make it a press pellet, you get even better accuracy. If you make it a fuse bead, because then matrix effects are avoided, you get the best accuracy. And for the liquid sample, because it is very homogeneous already, so you can directly put into the sample cup, no need of any of these preparation, and you get quite good accuracy for the liquid samples. This is one example of precursor material. So this is NMC hydroxide measured with epsilon 4. Measurement time is less than 4 minutes, and you can see all the peaks of nickel, cobalt, and other manganese. These are the three major elements, and then there are some minor concentration of other elements that are present. So these are the three major elements. And then you can make the calibration curves by having different concentration of nickel, cobalt, and manganese, a range of concentrations. So these are the typical calibration curve, and you can see that the linearity is quite good. This one is for the nickel, this one is for the cobalt, this one is for the manganese. And finally, this is what you can achieve. Once you have this calibration curve, you can measure your unknown sample. So in this case, we measured NMC 534, where nickel is about 50, supposed to be around 50%, and manganese around 10%, 30%. 53, it should be 532 actually, yeah. So 30% manganese and 20% cobalt. So this is what we achieved on this sample. So nickel was actually 58%, cobalt 23%, and manganese 33%. This is the XRF analysis, and this same sample was also measured onto the with ICP, and this is the concentration of given by the ICP. And here you can see that the XRF gives quite close to what are the actual reference values for this sample. Also, if you have a look at the standard deviation, the standard deviation for XRF is in fact less than the ICP. And this is because XRF is measuring the without any dilution. It is directly measuring all the elements at high concentration, whereas for ICP you have to do multiple dilutions, which affects your performance. So particularly for the major elements, XRF will always give you better values if the sample is well prepared. This is another example of NMC 622, and again here also you can see that the XRF results are very close to the reference values, and in different samples, and the standard deviation also is much less compared to the ICP. So this is the conclusion for this, that XRF, particularly if these are liquid samples and you are measuring the major elements, then it can give better precision compared to ICP. There is no sample preparation. In ICP, you have to digest the sample into acids and those kind of things. Here, you just put into the liquid cup and put it into XRF, and the measurement time is within 10 minutes, you have your results. This is another example where we measured the powder, NMC hydroxide precursor material. So not the liquid, but the powder this time. So here we made the fuse beads to achieve the highest kind of accuracy. So this is the fuse bead using we supply also the sample preparation equipment. And then after making the fuse bit, you can put either into GTM or into the epsilon 4. And in this case, we wanted to compare how the two behave, what kind of accuracies GTM gives and what kind of accuracy epsilon 4 gives. So this is the calibration curve. U for the different elements. This is for the nickel, I think, cobalt and manganese. So you can see again the calibration curves are quite good. These are the concentration ranges. And here this calibration standards were provided, made by us, because we have this lab where we can make this certified reference materials, and we also supply these. So this was calibrated using the standards that we made in our lab. This is the result on GTM, then on one of the few of the unknown samples. So these are the reference values, NMC 523, and these are the reference values, and these are the what we measured. This is another sample, NMC 811. These are the reference values, and this is what we measured. And you can see that the XRF results are very close to the reference values. And the standard deviation is also very less, because now it is calibrated with the certified reference materials. And these are the results with epsilon 4. Again, you can see that even with epsilon 4, the values are very close to the reference values. So you get very good accuracy, and also with the epsilon 4. Okay, so this was the part about the XRF. The other technique that you can use, and that is more of a R&D technique, but now it is also going into the quality control, that is the X-ray diffraction. X-ray diffraction is a technique that looks into the crystal structure of the material, and most of these battery materials are highly crystalline. So they have a given crystal structure. And the property of these materials depends on what kind of crystal structure or the crystal phase is present in this material. So XRD can look into this crystal structure, but not only this crystal structure, it can look into what kind of defects might be present in this crystal, because these defects also affect the performance of your battery. So it can look into the crystal structure, it can look into the crystal defects, and how these crystal defects are changing when you charge or discharge the battery. So this is the technique that you have, say, your sample. Again, mostly you measure it in powder form, but of course you can directly analyze the battery cell also, that I will come to that. So you put your sample into the diffractometer, there is an X-ray tube, there is an X-ray detector, very similar to what you have in XRF. Geometry is different, and here instead of white radiation, we use some monochromatic radiation. So sample is at the center. And once you measure with diffraction, you will get these diffraction peaks. And now these peaks don't represent elements, they represent a crystal phase. So whatever crystal phase you are having, say NMC 811, so all these peaks belong to not one peak nickel, one peak cobalt, one peak manganese, no. All these peaks belong to NMC hydroxide. So it is a, you can say, fingerprint of the compound, not of the elements. So whatever is the compound present, XRD tells about the compound. And this XRD pattern is related to the crystal structure, how the atoms are arranged into the crystal, which is a fingerprint of your sample. What you can do with XRD is you can do the crystal phase analysis. You can analyze the crystal defects. You can analyze the crystallite size, which are also in some way related to the crystal defects. And you can look at the crystal phase changes during charge discharge cycling. So let us look at the phase. This is, for example, NCM hydroxide, NCM 111 hydroxide precursor, and this is the XRD pattern. This is the XRD pattern for lithium cobalt oxide, lithium carbonate. So this is the XRD pattern, Li2CO3. This is the XRD pattern of the mixture of these two, NMC precursor and Li2CO3. So you get the peaks of NCM as well as the peaks of this Li2CO3. So mixer means it will be a mix of these two. But once you fuse them, you put this into oven and this lithium goes into this and becomes part of this. So this is the final cathode material. So then again the crystal structure changes and then this is the XRD pattern. So you can differentiate from the mixer that this is a mixer and this is the final cathode material, which you cannot differentiate with XRF. XRF, it is a mixture of lithium, nickel, cobalt and manganese. So whether it is this or this, it will give you the same information. But with XRD, because crystal structures are different, you can differentiate between the two. So one thing that you can use XRD for to ascertain that your reactions are complete and you don't have any reactants left over. So if you get any of these peaks which are present here, that means your reaction is not complete and you have to fuse this material even further. Another thing that you can measure with XRD is the crystallite size, which in a way represents one kind of defect. Say this is your particle. So your particle is this, and if you put it in, say, master sizer, this is the size you will get. But this particle may have these internal divisions, which are called the grain boundaries, and these grain boundaries are actually nothing but the defects in the crystal structure. So what XRD can measure is this crystallite size. So that means smaller the crystallite size, more are the defects in your crystal structure. If the crystallite size is same as the particle size, then there is no defect. So this is a perfect crystal, and then the performance would be the best. If the crystallite size is smaller than the particle size, then there are some defects. But smaller the crystallite size, more and more defects, and your battery performance will degrade. So even if you have the perfect chemistry, perfect particle size, everything is good. But if your crystallite size is very small, that gives you an indication that your battery performance will not be good. You have to make a material with crystallite size very close to the particle size, primary particle size. So this is one example of LMFP. So here lithium iron phosphate topped with substituted with different amount of manganese. So this is 20%, 40%, 60% and 80%. When you dope with manganese, the XRD peaks shift to the left, and shift to the left means lattice expansion. So lattice is expanding because of this higher manganese content. So that is kind of well-known phenomena, because manganese has a higher kind of ionic radius, and that is why the lattice expands. So you can measure how the lattice parameter is changing with the manganese content, and then this information you can use to qualify any of the unknown material. So you get, say, unknown material where manganese content is not known. You just measure the lattice parameter using the XRD, and then using this calibration curve, you can find out what is the manganese content. But apart from that, you can also measure the crystallite size. And in this particular case, we found that the crystallite size is increasing with manganese content. And as I said, increasing crystallite size leads to better battery performance. And it is known in the literature that if you dope with more manganese, then the battery capacity increases. So there are reports in the literature, and most likely it is related to one of the reasons. It might be because the crystallite size is increasing as you are having the higher manganese content. In fact, in your actual battery material, you are dealing with many different sizes. Your actual battery material, finally, what you will end up is with the aggregate. And this is the particle size that you measure when you put it into, say, laser diffraction. Master size is 3000. This is the particle size you measure, and that is typically between 2 to 10 micrometer. Then the primary particle size is, this is the primary particle, one of these particles. And this size is typically from 40 to 200 nanometer. And within the primary particles, then there can be internal division, and this is the crystallite size, which can be same as the largest crystallite size can be same as the primary particle size, but if it is smaller, then you know that there are defects. So we have different techniques. Here you can employ the laser diffraction, master size 3000. Here we offer DLS or small angle X-ray scattering on the XRD platform itself. And for this, you can use the XRD. So these were the two samples that we measured, and these are the, say, XRD size, crystallite size. These are the primary particle size given by the small angle X-ray scattering, and these are the aggregate size. So you can measure the whole length scale, and all these sizes are important. This size is important because this governs your packing density and other things, and the power density and the power density and the energy density. And this size determines your diffraction to the crystal and the battery performance. Another thing that you have to take care when you are researching on new battery materials is another kind of defect that is called the cation mixing. Cation mixing is a defect which is very at the atomic level, and normally you will not know about this, but only when you make the battery, you will find that your battery performance is very low. And that may be caused by this cation mixing. Cation mixing is that if you have a look at the crystal structure of, say, NMC, then you have this oxygen layer, and then you have this in this direction when you're looking, 001. Then you have the NMC, nickel, cobalt, manganese layer, another oxygen layer, then you have the lithium layer, NMC layer, lithium layer, NMC layer, like this. What cation mixing means is that the lithium and nickel get mixed up. So lithium from this layer can go into this layer, and nickel from this layer can go into this layer. So when they get mixed up, that is called the cation mixing. For a good performance, there should not be any mixing. This layer should remain separate. But once you have this cation mixing and it is at atomic level, there is very difficult to find out that this is there, and only XRD is the technique that can tell you. So we can find out with XRD because this is a kind of defect in the crystal, and XRD has a signature in terms of the relative peak intensities. So once you measure the XRD peaks, so there are two peaks. One is the peak coming from this plane, which is the 003 plane, and another is this plane, which is the 104 plane. So another peak, which is 104. So in this layer, you can see that if you talk about this direction, then lithium and nickel are already mixed. So in this, you have both the lithium and nickel present, but in this direction, they are separate. So if there is a cation mixing, this layer is not affected because here it is already mixed, but these layers are affected. And so by taking the ratio of the peak intensities of these two, you can find out how much is the cation mixing. For example, if there is no cation mixing defect, then the peak ratio of these two is, theoretical peak ratio is 1.35. If you have cation mixing of 20%, then it reduces to 0.56. So using this number, you can find out how much is the cation mixing, and that might be the source of your battery performance degradation. And then you have to improve your material that these defects are not present. So the way you synthesize it, the way you anneal it, how much time, what should be the ramping up time and other parameters. So you have to do something to improve that crystal defect. Finally, let me have a look also how much time is left. Okay, we have time around 15 minutes. Finally, I come to the inoperando XRD. Other thing that you can do with the XRD is you can put your battery cell, you can make a test cell, which can be either a pouch cell or it can be a coin cell. But if it is a coin cell, of course, X-rays cannot pass through steel casing. So if you are making a coin cell, the one side of the coin cell should be with a Kapton window. So you punch the hole in that steel casing and fix a Kapton window with some glue, and then you can use that for the XRD. Or we also provide electrochemical cell. It is same as the coin cell, but then if you don't have, say, facility to make the pouch cells, you don't have the facility to make these coin cell, then what we can do, we can provide you a electrochemical cell. So in this electrochemical cell, you can put your same, whatever you are putting here, your electrodes, the cathode material, cathode, the anode, the separator, and the electrolyte. You can assemble this electrochemical cell into a glow box. So you open this into a glow box, put your electrode materials, separator, and the electrolyte, assemble it in the glow box, take it out, and put it on XRD. So it is like a coin cell, but it is reusable, has beryllium window, and you can use it multiple times for different kind of your research chemistries. What you can investigate with the XRD is one of the major cause of battery degradation with cycling is the particle cracking. So with cycling, slowly these particles which are coated onto the current collector, they start cracking. And once they crack, they come off the electrode, they go into the electrolyte, and then they try to migrate here and there through the separator. They corrode the separator, corrode the electrolyte. So once you have this particle cracking, then your battery starts degrading. Another thing can happen that this lithium ion go into the anode, but then they cannot come out. Only some of them come out, maybe 60% come out, but 40% get stuck into the anode because your anode had a lot of defects and it trapped those lithium ions. So you can investigate that lithium retention. If you are doing very fast charge, then lithium can also do plating. Instead of going into the anode, on the surface of it, lithium gets plated. And then you have a layer of lithium, which is not contributing to any energy density, and then it is lost out of the system. Or any undesired kind of phase formations, because during some materials may not be stable with voltage. So once you apply the voltage, they change the phase, and that phase is no more stable or no more suitable for lithium ion movement. And then again, your battery can degrade. Okay, so these are the different geometries that you can employ. This is the pouch cells. So for the pouch cells, we can supply you a holder. Then you can put your pouch cell, and you can do it in the transmission geometry. Or if you don't have that, we can provide you this electrochemical cell, and then you can assemble your cell into this electrochemical cell, and then you can do in the reflection geometry. This is an example of in operando charge discharge cycle. So here, this is NMC 333. This was a pouch cell about 5 millimeter thick. Every scan is 5 minutes, and we did 4 charge discharge cycles here. And it took about 4 hours. So 0.1 C rate. So in this, we use here, because it was a thick pouch cell, we use the silver radiation. We could capture around 20 peaks in this range. So the peaks that you see straight, these are the current collector peaks. This can be aluminum or copper, but the peaks which are changing are the anode and cathode peaks. So this is a zoom out of that. And then this is the cathode material peak. Now you can see that with discharge, this is the 2 theta. So this peak is moving to the left. This is the isoline plot. Color represents the intensity, and the position represents the 2 theta angle or the lattice parameter. So if it is moving to the right, that means lattice contraction. So lattice is contracting, and if lattice is contracting, your particle will also contract. If it is moving to the left, that means lattice expansion. If it is lattice is expanding, your particle will also expand. So in a way, it is looking at your particle, how your particle is breathing. So it is expanding and contracting and expanding and contracting as you charge and discharge this cell. If it is doing it slowly, if it is breathing, these particles are breathing slowly, they are expanding and contracting slowly, then nothing will happen. They will not crack. But if this expansion or contraction is very rapid, then it will put a lot of stress onto the particle and then the particle will crack. So you can look into this behavior, whether they are doing it very fast, expansion and contraction, or they are doing it slowly. In case of NMC 333, they are doing slowly, but once you have, say, NMC 811, you will immediately find that, oh, this lattice expansion is very rapid. And that is why NMC 811 chemistry is not stable. You have to really make some special design of this material to make it stabilize these particles. Otherwise, if you make it just like that in the lab without any design, then initial performance might be good, but after a few cycles, you will find that performance degrades. Usually what in the design, what they do is they do the grading. So the nickel content is changing from the center to the surface of the particle. So instead of having the whole particle with homogeneous 80% nickel content, they will do the grading. So the nickel content, as you come to the surface, it becomes lower and lower. And that is why, because at the surface, the nickel content is lower, so the particle gets more stabilized. And then there is some designing aspect, how you produce this graded kind of particles. Anyway, so this, on the other hand side, you can look at the anode. In the anode, when it is fully discharged, then this is graphite. So this is the graphite peak here at 9.5. When you start charging it, it converts to lithium carbon 12. And the peak moves to 9. So there are one lithium atom corresponding to 12 carbon atom here. If you charge it further, it becomes lithium carbon 6. And that means one lithium atom corresponding to 6 carbon atoms, so more lithium. And the peak moves to around 8.6. So from this peak position, you know that, okay, this is lithium carbon 6, this is lithium carbon 12, and this is lithium carbon, this is pure graphite. And when you discharge it, again, it goes back from lithium carbon 6 to 12 to pure graphite. And this cycle keeps on repeating. But however, in the discharge state, if you find that this peak is still persistent, that means some lithium ions are retaining, they are not going back to graphite, they are retaining into the carbon matrix itself, or if this peak is present. So using this, then you can find out if there is a lithium ion retention. Using this parameter, you can find out whether it would have a tendency to particle cracking. If there is a lithium plating, then you will see another peak, set of peaks that are appearing and which are related to the lithium metal. So you can, without opening the cell, just by doing the in operando XRD, you can find out what is happening inside the battery. So you are not opening it, you are doing the full cell and just doing the in operando charge discharge. This is the typical XRD pattern. Then because you always have, apart from isoline plot that you can do in the software, you can also analyze each of these patterns separately in more detail. For example, you can try to find out what are the phases present. So for example, here, these are the phases present, lithium metal oxide, copper is the current collector, aluminum is the current collector, and then the three phases of the carbon, the graphite, lithium carbon 12, and lithium carbon 6. And at a given state of charge, you can find out how much is their relative concentration. You can also do, because this has a huge number of data, you can in the software you can do statistical analysis that what are the microstates this material is passing through. So in the fully charged state, this is the microstate, and then it is passing through different microstates, and finally this is the microstate where it is in the fully discharged state. And then you can analyze these different charge states separately using the read belt. So this is one example of the complete 160 scans, and now you are quantifying for each charge state how much is the lithium present. So this is the fully discharged, fully discharged state. In the fully discharged state also, you see that there are around 10% of lithium that is present. Ideally, it should be 0%, but even in the fully discharged state, so some lithium is getting retained into the carbon. Into the fully charged state, it is about 60% lithium carbon 6, and rest is 40% is lithium carbon 12. That is in the fully charged state. That means it can take more lithium atoms, and usually anode has a higher capacity than the cathode materials, at least the current cathode materials, and that is why graphite is good enough. But once you move into, say, solid state batteries and those kind of things, then you may need better quality anode materials. Now on our XRD platform, we also offer new stages for this in operando XRD, and that is the variable temperature stages. Because what happens that, say you are working on a new battery material, and you make the battery, you do in operando cycling and you do other tests, and you find that at room temperature, your battery material gives very good performance with cycling. But you have to also test what happens if battery is heated to 50 degrees centigrade. Because when EV is running, during the running it is discharging, heat is produced and the battery can get heated up. So you have to also see whether it is behaving properly at higher temperature or lower temperature. Say these the battery that you are making, they are sold into countries, colder countries where the temperature can go down to into minus. So whether the performance remains the same or it is only at room temperature, it gives good performance, but not at other temperatures. So that environment now you can simulate onto the XRD itself. We provide these chambers where you can put your pouch cells or the electrochemical cell. You can heat it up to 70 degrees centigrade, cool it down to minus 10 degrees centigrade. And at different temperatures, you can do in operando XRD. And then you see whether with temperature, whether these materials are stable or not, and how good performance they are giving. We also, if you don't have the pouch cell making facility, then we provide this electrochemical cell. This is the kind of electrode that you prepare, just like the coin cell. And then you put these electrodes into our electrochemical cell that we provide into a glove box, and put then after assembling the cell, you bring it to the XRD. And then again, you can do the charge discharge cycling. And also this is variable temperature. So you can investigate your battery from minus 10 C to 70 C in this temperature range with in operando XRD. This is how it works, that you have this stage VTEC trans, for example, mounted onto the XRD platform. This is the temperature controller. This is the potentiostat that is connected to this to charge discharge the cell. And everything is then controlled by the software that we provide. So the temperature controller, the potentiostat, and the XRD, they're all controlled by this control software. So it is a single software. You don't have to use 3 different software. So it is a fully integrated solution which controls everything, and then everything is written into one file which opens into our analysis software. So you have all the information. So this is typically how it looks. So you can make your charge discharge cycling at different temperatures so very easily. And you can define you want to do at constant voltage, constant current, open circuit voltage, and how you want to charge your battery and how you want to discharge it. So you have the full liberty to make it, and it is just a drag and drop. So very easy to make these charging discharging programs, and then you get this XRD data. Okay, finally 2-3 slides about the instrument, XRD instrument. We have two types of instrument. One is the compact XRD. This is called the Aries compact XRD. This is 600 watt, and this XRD is present in our DKSH application lab. So if you want to have a demo, you can come to our DKSH lab and you can have a look. Here you put the samples outside. You don't have to open the cover. You put your sample and it will be automatically loaded onto the diffractometer. It doesn't require any peripherals like the water chiller. It is just plug and play. Mainly this is for powder diffraction. So when you are making this NMC materials, or the graphite or the anode materials or the cathode materials, you can check it. But this can also do limited inoperando. That is on the coin cell. If you are making coin cells, we can mount these coin cells onto Aries and you can do inoperando. It can handle various sample sizes, the small quantity powder up to microgram, up to milligram, regular sample holder, polymer samples, fibers, piece of solids, glass slides. So different kind of samples you can mount on Aries. This is our flagship Empyrean XRD platform, which is a multi-application platform. You can do powder, you can do thin films, you can do nanomaterials analysis, and also the inoperando XRD. So here the inoperando XRD you can do with in situ heating and cooling. So from -10 to 70. It has very high-end configuration to give you very good quality data, very fast measurements. So we can do measurements. We have provided a solution to LG Chemicals for their QC application. So every XRD pattern we can measure just in 10 seconds. So it is a very fast, you can do really very fast inoperando XRD measurements. Okay, so on this Empyrean platform, again, these are some more internal details that we have some new possibilities that we have the multi-core optics. So it is a single optics for many sample types, whether you have powder, thin film, solid, nanomaterials, particularly if you are in a university, you are dealing with a lot of variety of samples apart from battery. So this is a platform that can automatically analyze all these materials without any manual user intervention. So if you have many students using it, you don't have to worry about they will change the optics or they will mess up with the optics or something will happen. Nothing will happen because no manual intervention. It is just from computer, you tell your sample and it will analyze your sample. And the wonder detector is for very high resolution, very low, high sensitivity data. This is one example of one sample where you are having the chromium and copper present in your sample. If you measure with the standard kind of diffractometer, this is what you get, very high background. If you measure with a energy dispersive detector, then this is what you get. But with our system, which has the multi-core optics and the energy dispersive detector, you get very low background. So the peaks that you don't see here, you can see those peaks here for the minor phases. So if there are some small phase transformations that are happening because of the charge-discharge cycling, and small phases are appearing, with this optics, you are able to see those small phases. Okay, with this, I will stop it here. Thank you very much for your kind attention and for coming here for this seminar. Any question, please feel free to ask. Or you can also ask during our break time.